There is another equivalent way of looking at this the CTMCs that I want to talk about. So, we have talked about the embedded DTMC with transition probabilities Pij and holding the exponential holding times of rate nu I if you are in state I, right. An equivalent way of looking at it equivalent way to look at a CTMC. So, let us say, so you have these nu i's, right, for each state, right, which are exponential, right, and Pij which is given to you, right. Now, you define Qij equal to nu I Pij, okay. I am just defining something. Qij is equal to nu I times Pij. Now, what does this Qij represent, right? So, you can view this Markov chain CTMC as being spending an exponential amount of time nu I in each state and then going to some state j with probability Pij, right. So, you can look at this nu I times Pij, which is now our Qij, as the rate at which transitions happen from I to j, right. So, Qij can be interpreted as the rate of transitions from I to j, all right. So, an equivalent way to look at this is that let us say this is my CTMC time axis, okay. Let us say that xn minus 1 is equal to I, okay. Now, so obviously there is a, so one way to look at it is that there is a exponential of rate nu I which is about to fire, and after the end of the exponential I will go with probability Pij to state j, right. And yeah, so you can say that xn equals j with probability Pij, right. This is one perspective. Another perspective is to say that okay, I am in state I, xn minus 1 I got to state I. Now, there are a whole bunch of competing exponentials with rates Qij, okay. So, whenever you are in state I, right, think of Qij where j runs over all the other states, okay, as being competing exponentials, right, independent competing exponentials, okay. Now, so these Qij's, you fix an I, these Qij's where j runs over all the other states are and you think of these exponentials of rate Qij as competing, okay. Now, whichever exponential wins, okay, you go to that state, all right. Now, what is the probability that of all these Qij exponentials which are competing, they are independent exponentials, what is the probability that a particular exponential into state k wins? It will be Qik over sum over all the Qij's, correct. Now, what is sum over all the Qij's? Sum over all the Qij's is just nu I, right. So, yeah, note sum over Qij of all the other states is just nu I sum over Pij sum over all the states, which is just nu I, right. So, you have these all these Qij competing exponentials, right. So, let me say I am in state I, okay, at xn minus 1. So, I can have competing exponentials independent exponentials of rate Qij j belongs to the states, right. Now, what is the probability that I actually transition into a particular state, let us say k, right. The probability that the kth exponential wins is nothing but Qik over sum over all the Qij's, right. Sum over all the Qij's new I, right, as we just saw, right. So, it is the probability that the Qik exponential wins will be Qik over nu I, which will be Pik, correct, which is the probability of transition into state k, right. So, instead of having an embedded Markov chain with transition probabilities Pik and this holding time exponential which is nu I, you can equivalently think of, you can forget about the Pij's, you can just say I have independent competing exponentials of rates Qij, correct, and this Qij sum to nu I, alright. So, this is basically like splitting and merging of independent Poisson processes, if you will, right. So, this perspective is also equally valid, right. You can either have exponential holding times and then Pij transitions, or you can just have Qij exponentials, independent exponentials, where j ranges over all the other states competing. Whenever you are in state I, you have independent competing exponentials of rate Qij, okay. So, if you go back to the MM1 example, these are the nu i's, right. What are the q's? Qij, right, if for this example Q01 will be lambda, right, Q12 will also be lambda and so on, and Q10, Q21 all that will be mu, Q32 all that will be mu, right. So, Qij is just nu I times Pij, you can look at it that way, or you can look at it as whenever I am in state 0, I have only one exponential, a lambda exponential. In all other states, I have a competition between the arrival exponential and the service exponential, right, which are of rates lambda and mu respectively, okay. So, in any CTMC, this perspective is valid. You can just say that whenever I am in state I have competing exponentials Qij, for every state j there is an exponential Qij independent for across the states, and whichever exponential wins I will transition to that state, okay. And we know that the probability of transitioning to that state will be according to competing Poisson processes, it is basically Qij over nu I, okay. And conditioned on transitioning to one of these Qij exponential winning, the holding time is still exponential with parameter sum over Qij, that also we know, right, from Poisson processes. So, it is back to our original perspective. It is not as though if the jth exponential wins versus if the kth exponential wins, the conditional holding times are no different. This is a fundamental property of the Poisson process, if you remember, if you can go back and check if you want, right. So, if the jth exponential wins, the conditional holding time is still exponential of rate nu I, it is not exponential of rate Qij, okay, because all these it happens to win among a bunch of exponentials, right. This is a fundamental property that we have covered, we have studied in Poisson processes. Okay, so, these are two equivalent perspectives, right, and depending on whichever exponential wins, you go to that state. If jth exponential wins, you get xn is equal to j, and this holding time will be, you can show that it will be exponential with parameter sum over Qij, which is simply nu I, all right. Good, this is just a equivalent way of looking at CTMCs. There is one more concept I want to introduce, which is time sampled Markov chain. See, this is the perspective here is that, see, I have a CTMC. Now, I am going to divide time into some very small intervals of time delta, okay, and look at what really happens in these small time intervals. Okay. So, I am going to divide time like this, little deltas, right. Time is continuous, the CTMC after all, but I am going to divide my time into these little delta intervals. Okay. Now, I am going to look at what happens, how do these transitions happen in these little delta intervals. Okay. Suppose at some particular, so and I am going to call this maybe I should call this see, I do not want to call it x again xns, because xns are the embedded Markov chain, right. Now, this is a time sampled approximation. This is also will turn out to be a DTMC, but it is a different DTMC from the embedded DTMC. Okay. This is the sample time approximation to the CTMC. Okay. So, maybe I should call this x of 0, x of delta, x of k delta, and so on, right. So, okay, let us say that I am in some state I, okay, x of k delta is equal to I am in some state I. Now, what is the probability that, let us say, in another little delta interval, what is the probability that I go to some state j, right. If I look at this probability that x of k plus 1 delta equal to j given x of k delta equals I. Of course, I can also condition on the previous guys, right. I can also talk about what happened in k minus 1 delta and all that, but because of the Markov property, all that is irrelevant. We already know that I can just take out all the previous conditionings. Only x of k delta equal to I, that is the only thing that matters, right. So, you can clearly, I mean, you can easily argue that this process satisfies a Markov property in this index k, right. Whenever you are looking at these tiny time intervals delta, there is a Markov property, and what is this equal to, right. So, this is the probability. So, remember now we can look at this competing exponential perspective. So, you are at x k equal to x of k delta equal to I, it does not matter how long you have been in the state I, because the exponential is memoryless, right. So, now you have a bunch of competing exponentials, right, all these qij exponentials, correct. You will have probability of x k plus delta k plus 1 delta equal to j if the qij exponential happens to fire in this little delta interval, correct. And of course, the probability of two exponentials firing in this little delta interval is very small, it is little o delta, right. So, this can be written as qij delta plus little o delta, okay. So, qij times delta, I mean, if you ignore this little o delta term, qij times delta gives you some kind of a transition probability from state I to state j in these tiny little delta intervals, okay. So, you can view the Markov chain, right, you can view the DTMC, which is the process x of k delta, okay. See, remember this x of t is the CTMC, I am looking at the CTMC at these k delta intervals, right. X of k delta, where k is greater than or equal to k takes non-negative integer values, right. Let me write it as z plus. It is of course a DTMC, has transition probabilities qij delta plus little o delta, right. We are going to assume all qij's is less than some b, okay, which is finite, okay, for all ij. So, remember this state space can be infinite. So, this qij's could potentially become very large, could become unbounded, right? There is an infinitely many of these qij's. So, we are not going to consider those kind of processes, we are going to stick to Qij's being upper bounded by some number b, right. It could be 100 or 1000, I do not care, but it is something finite, right. So, I can take delta small enough, right. You take delta small enough such that Qij times delta is a valid probability, right. You should obviously Qij times delta is bigger than 1, this is not, the delta is too big, right. You take a small delta and you can fix a small delta such that Qij times delta is a valid probability, okay. And then Qij times delta becomes the transition probability matrix of this time sample DTMC, okay. Now, what is the probability? And similarly, you can say what is the probability that x k plus 1 delta equals I given x k delta equals I, that is the probability that you are in the same state, right. So, you are going to some other state with probability Qij times delta plus little o delta, and the probability of not going to any of the other states will simply be the probability that none of these exponentials, competing exponentials actually successfully fired in that little delta interval. That will be, you can say it will, you can prove this, it will be sum over j Qij times delta, okay, plus little o delta, which is nothing but what is sum over Qij? It is just nu I, right. So, 1 minus nu I delta plus little o delta, okay. So, if you look at this time sample Markov chain, right, you have transitions to state from state I to state j with probability Qij delta in this little delta intervals, and no transition to some other state, is basically you remain in the same state with probability 1 minus nu I delta plus little o delta. So, remember that, so there is a, see in the time sampled approximation, I want to make this very clear, in the sample time approximation to the CTMC, which is this DTMC, will have self transitions, alright. We said that the embedded DTMC does not have self transitions, alright. This is just a self, so this term is in fact a self transition term, right, between k delta and k plus 1 delta, and it will have a substantial probability of 1 minus nu I delta, because there is a substantial probability of none of these exponentials actually firing in this little time interval, right. So, the basically there are two DTMCs, one is the embedded DTMC, which looks at only the transitions at state changes, and there is a sample time approximation which looks at the progression of the process at these little tiny delta intervals, and this sample time approximation, which is a DTMC for some small delta, will have self transitions, right, and its transition probabilities are given by Qij delta for other states j and 1 minus nu I delta for self transitions, okay. The embedded Markov chain does not have self transitions. I hope this is clear, okay. Now, for the embedded, so we know that for the embedded Markov chain you can find some pi i's, right. Now, for the time sampled approximation, which is a different DTMC with transition probabilities Qij delta, you can also find its steady state probabilities, right. The question is, are they the same, right. The transition probability, you have the embedded Markov chains transition probabilities from which you can find some pi i's, which we already did. We said the pi i's represent the average fraction of transition into a particular state. Now, we have a different DTMC, right, which is the time sampled approximation. You have all these little deltas and look at the transitions. You can go ahead and calculate the steady state probabilities of this DTMC also, right. Are they the same as the steady state probabilities of the embedded Markov chain? The answer is no, okay. In fact, we will see that if you write out the transition probabilities of this time sample Markov chain and work out its steady state probabilities, you will in fact get the average fraction of time spent in state I, okay. If you solve for the steady state probabilities of this particular transition probability matrix in front of you in the screen, you will in fact get the fraction of time spent in state I. Whereas, if you solve for the steady state of the embedded Markov chain, you will get the fraction of transitions into state I, okay. So, there are two different things, Okay. So, we will see this in more detail. At a high level, I just want you to understand that there are two different DTMCs corresponding to a CTMC. One is the embedded Markov chain, other is the time sample Markov chain. Okay. And their steady state probabilities are different, they are not the same, and they may mean very different things. Okay. Okay. So, today we will stop here.